Hello and welcome to CMOS system-on-chip-based radiometric and spectroscopic instruments for space exploration with Dr. Adrian Tang. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by MTTS. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archive webinar goes up, so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the Live Slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. Now let's introduce our speaker. Dr. Adrian Tang has 17 years of CMOS and SIGI IC chip design experience in both research and commercial wireless environments, with projects ranging from the design of commercial Bluetooth and WLAN chipsets to millimeter wave and terahertz spectrometer systems on chips to detect signs of life on other planets. At NASA's Jet Propulsion Laboratory, Adrian directs the Space System-on-Chip Laboratory and is currently leading development of a wide range of CMOS SoCs for planetary science instruments exploring the solar system, radio telescopes for astrophysical studies of our universe, and earth science instruments to understand our planet's changing climate. Adrian completed his PhD at UCLA in 2012 before joining JPL in 2013 as a strategic researcher. Adrian was awarded the SPIE Rising Researcher Award in 2016 for his work on millimeter wave radiometers, the 2016 NASA JPL Explorer Award, and 2016 NASA R&D Research Award for his work on CMOS gamma radiation sensors, the 2017 NASA Innovation Medal for his work on self-calibrating instrument systems, the 2018 NASA Voyager Award for his work on 600 gigahertz spectrometers, and the 2019 UCLA Rising Professional Alumni Award. Adrian is also a senior member of the IEEE. Now it's my pleasure to turn the virtual podium over to Dr. Tang for CMOS system-on-chip-based radiometric and spectroscopic instruments for space exploration. Adrian?
All right, good morning. It's Adrian here, and I'm going to talk about radiometers from California, which is not currently on fire near me, but coming soon. All right, so, wow, I have a title slide too. Okay, so yeah, radiometric and spectroscopic systems. So I think the first thing to do is remind us how these things work, or introduce how these things work if we're not familiar. So a quick refresher. Oh, God. Okay. So microwave radiometers are receivers that basically are used to detect differences in temperature. So it's not like temperature, like when you burn your hand. It's temperature with emissivity factored in. So how much, black body radiation something's emitting. So here you have like two receivers with the mouse that you can't see that I'm pointing at. And what happens is as you go from temperature 1 to temperature 2, this receiver should be able to see the difference between those two temperatures. This is not super complicated. So it's much simpler than radar as your other remote sensing instrument. It's just basically a remote thermometer. One of the interesting things is a lot of gases, they don't emit white black body radiation. They emit spectrally shaped black body radiation because of their molecular resonances, the rotational resonance, actually. So what happens is you can actually see these lines show up in the floor, in the noise floor. So you can use these to identify what chemicals are what, or try to figure out what these gases do or where they come from, or detect them around other planets or neat things like that. So how you do that is with a spectrometer, which is very similar to a radiometer. So this is the two side by side. The radiometer is the top one. And what happens is you have a receiver and you integrate up power and you get a single number for like how much power the receiver is seeing. Spectrometer is almost the same thing, except you frequency resolve it. So you like put the receiver pointed at something and say how much power is coming in at each specific frequency, which is a bit different. Typically the radiometer one is like analog, simple, direct detection. The spectrometer ones are usually heterodyne because you want to keep good frequency resolution. You don't typically do a direct detector spectrometer. So heterodyne is usually the way we go with these. Things we do, one thing that we do with these is we sound the atmosphere. So by setting our receiver up at certain places where there's certain lines of interest, which tell us things about Earth's climate, we can do a sounding. We can look at the radiometric brightness. We can sort of tell, in a second to minute time scale what the abundance of a gas is, like water or ozone or something, or oxygen. We can get the pressure by how broadened it is. We can use a weighting function, which tells us it's like a weighting function of what the atmosphere should look like. And that can tell us what's going on at each altitude and give us altitude resolved measurements. All that's super useful. Another thing we can do is we can look at isotopic ratios. So this is an example here. This is Moreau, which looked at P67, which was a comet, and you can see regular water and heavy water. And one of the interesting things is that the ratio of heavy water to regular water was not what was expected. So the cool thing is that, spectrometers are able to distinguish different isotopes. So you can talk about, from central limit theorem, if you have a sample of water or something, how much, is it from a common source because it has the same isotopic ratio or not? It's kind of cool. Another thing you can do is gas dynamics. So this is one of my favorite things that I learned about since I got to JPL, which is this weird hexagon on Saturn's pole that nobody really understands how it works, which is upsetting. And what we can do is we can look at what the particles are doing, what the temperature profiles look like, and then we use a Doppler shift on the spectroscopic lines to find out what the velocity profile is of all the particles in the hexagon. Maybe we can learn something. So here's some things you need to know about spectroscopy. First of all, it doesn't work at room temperature. So if you have a warm gas in front of a warm background, there's no contrast because the warm gas emits its spectral lines at the same temperature as the warm background, so you literally see nothing. So that's not good. So the first thing you do is you need to go somewhere cold. You need to have a cold background. So you have to look at a warm gas against a cold background. On Earth, what we do is we limb sound. So we look at a squinted angle at the atmosphere and with the cold space behind it, and then you can see something. So these spectral lines start to pop out and you can see something. So cold background, very important. Okay, here's an example. These are some water bottles in the lab. And one is a hot water bottle and two are room temperature water bottles. And the room is also room temperature, it turns out. So then you can't see any bottles because there's no bottles because they're the same temperature as the background and there's nothing to see. So that's the whole thing about radiometric contrast. That means that if you're doing passive imaging, good luck to you indoors. Without a cold background, there's not much to see. The second thing to think about, or third thing to think about, is pressure broadening. So when you put pressure on a gas, you're kind of dampening the molecular resonance, and then you can't see a line anymore. So you can't do these things at standard temperature and pressure. There's nothing to see. The line is squished out of existence. The cube comes down and down and down, and then it's gone. So what I'm basically saying is you have to have, cold background, and you have to have low pressure. So the other way to say that is it has to work in space. It doesn't work very well in, a standard room or, Earth environment. Okay, so NEDT requirements. This is kind of the core of the thing. NEDT is the noise equivalent delta temperature. It's the temperature that the receiver can resolve between two targets. And it's not an easy thing. So climate studies around here at JPL typically are asking for half a Kelvin NEDT. If you want to look at water and atmospheres where it's colder in the background, you can get away with a little bit worse, maybe 1 Kelvin. But you have to think about what that means, right? So if you have a 3 dB noise figure in your receiver, that's 289 Kelvin. And you're trying to pick out the difference between 289 Kelvin and 289.5 Kelvin, which is not a big difference. So if your receiver is doing this measurement and then suddenly your gain changes by, say, 0.5 or 0.007 dB, I have it there, suddenly your measurement's no good because the temperatures you were looking at when you started and the temperatures you looked at when you ended are different. So the instrument calibration is super duper important. And there's a lot of reasons that the receiver might change by that 0.007 dB. And not all of them are electronic. Of course, you have flicker noise, and flicker noise is sad, and it changes your bias conditions over a long time. But you also have thermal changes. The receiver might change temperature. You might drop it, or kick it, or bump it, and then that changes the gain. You might have a change in your supply conditions, or you might have other low-frequency noises nearby, or coupling, or whatever. So that's the thing that you have to deal with. And the way we usually quantify this is with Allen variance. So what I have here is I have a raw radiometer output. So it's just the output recorded from the receiver with a power detector over a long, long, long time. And if you look at this time slice I take, if you calculate the error, like, so you have a mean value, which is the dashed line that I'm pointing to that nobody can see I'm pointing to. And what happens is you have some value. And if you increase the time you look at, you actually get a better value because you're averaging over more points. And this keeps going and going and going, and the situation gets better until the long-term underlying drift makes things worse. So, like, here it's getting better because the mean in this section is pretty much all the same. But once it starts to drift away, the variance of the measurement starts to get worse and worse, and then worse and worse and worse. So what happens is you can't integrate forever. Eventually, you're going to bump into the Allen variance. Then your receiver's going to drift, and your measurement's no good. Cool. So what you end up with is usually a plot like this on the left. So as you integrate, this is just showing at the x-axis as you integrate longer and longer and longer what your error is in your measurement. So it gets better and better and better and better and better. And then at some point, it starts getting worse and worse and worse again. And, commonly people call that bottom, where the left is kind of your noise, right? It's the short-term drifting, and the right is short-term noise. The right is your long-term drift. And somewhere in the middle, they kind of agree in their minimum. So when you have the minimum contribution measure, we call that the Allen time. And you can, if you know the traditional radiometer equation, you can see those two terms. The red one that I've highlighted is the noise term, which is that short term, you average longer, things get better. And the blue one is that, like, things slowly drift away and make you miserable. So that's that. Okay, so why would you want to do radiometers and spectrometers for space? Well, there's a few basic reasons. You don't have a lot of power in space, especially in the outer solar system. When you go far, far away, the sun gets really, really small. And then the solar panel, it doesn't do so well. And you don't have a lot of power for your instrument. And if you go nuclear like North Korea is trying to, what happens is you're going to run out of power from your reactor or your RTG because you can't carry that much mass. You can't make an infinitely big reactor and stick it in a rocket. So whichever way you do it, you're going to run out of power. So power consumption is everything. The other thing is, rockets are big, but the actual part going to space is pretty small. So you like compact and highly integrated things. Kind of good. So that's why, CMOS is a really good solution for this, maybe if it can work, because we can make very, very complicated things very, very small, work very, very well. And maybe we can make instruments out of them, which is my whole work here. So the first question is, can we deal with the RF? So I always show this slide. These are like other technologies floating around JPL that are all much better than CMOS. Gas Shockey and SIS and the nice MIMIC technology, they have much, 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 much more sensitive receivers than we could ever make in CMOS. So the idea that we're going to displace these people with the CMOS chip is silly. So we have to find a role that makes sense. Where we can still reduce the size, weight, and power. So the ones we focus on are basically support systems. So the LO generation of these things, maybe a little bit the back-end processing. Also, we focus on active instruments like radars a little bit where you don't have a noise limitation. And then we look at hybrids a lot too, where we mix two technologies. So we have indium phosphide and something else. Going to space with a chip is not easy, of course. You have to worry about radiation because the radiation will kill your chip and it's depressing. If you go to places like Jupiter, the radiation is really, really high, and you're talking about like 50% changes in transistor thresholds and horrible things like that. The other thing is the temperatures are all over the place. The Earth is probably the most benign place in the solar system. Everywhere else is too hot or too cold. So you need your chip to deal with too hot and too cold. So those are the things you're always thinking about when you're thinking about saying, we're going to put a CMOS chip in space. You don't address those design problems, nothing's going to work out for you. All right, so CMOS radiometers and spectrometers. This is a fun slide. So this is not new. People have been doing radiometers and CMOS for a long time. A really long time, actually, almost 10 years now. More than 10 years now. So one of the things that you see is all these groups reporting these things, they don't actually have a lot of radiometric measurements. And I put myself up there with the yes, but it's bogus yes, because ours are hybrid systems with indium phosphide front ends. So I've been looking at why people don't get the NEDTs that they think they're getting or calculate that they're getting. And usually it comes down to this. A lot of people in the literature, and I stole some paper snippets here on the left, people assume that the drift goes away when they put a Dickey switch or some kind of calibration, but there hasn't been a lot of people quantifying that, and I think that's why the reported results aren't able to produce radiometric measurements, only like measure the noise figure, calculate the NEDT, and report that. Dickey switching, if you don't know it, is a double correlated sampling trick. So what you have is you have a resistor up front in your receiver, and you switch to the antenna, and you switch to the resistor, and you go back and forth, and you can basically de-embed the drift of the receiver over time because you have these cal measurements interleaved with your signal measurement. So that's pretty good. We built one, and it was bad. So we calculated from the noise figure, from all the stuff, assuming delta G over G goes to 0, that we should get about 1 Kelvin. When we measured it, we got about 38 Kelvin, NED delta T, which is bad. That's almost completely useless and a waste of money. So we spent a lot of time trying to figure out, hey, why did we waste this money? And we found a couple of things. First of all, in CMOS, the flicker corner is high. That was a 65 nanometer CMOS, which has a flicker corner about 1 meg. So the switching back and forth isn't great. You can go that fast, but it's not a good switch. The second bigger problem is the receiver bounces. When you switch the switch, the whole receiver goes through transients. But it's not just like the RF nodes that have the big bandwidth. It's like all the nodes. They bounce up and down. So you basically are like trying to do a super sensitive 0.007 whatever dB measurement on a receiver that's bouncing up and down. So that doesn't really work. Also, there's a 50% penalty because you're looking at that resistor half the time. So that's disappointing. So the next thing we did is we built a 15 gigahertz CMOS one where if you look on the left, we put an indium phosphide amplifier out front to push down the T-sys so that basically the noise figure is not dominated by the CMOS part. And that seems to work really well. So we got a TA that was a little bit better than what we got before. The Allen time's about 1.5 seconds. In terms of NEDT, we did a radiometric measurement. So what we did is we stared into a hot absorber and a cold absorber, and we just looked at the variance of something that's not changing temperature. And, sure enough, 0.5 Kelvin, 0.6 Kelvin, something like that. It's workable. It's not amazing, but it's a good start. The next one we came up with was this one, which is a Dickey-free radiometer, or some people call these correlating receivers. And they're confusing, but how they work is they have 2 receivers and a microwave hybrid up front. So it's like the signal is on one phase and the cal is on the other phase. And the way to think about it is the I of one signal is the Q of the other signal, and the Q of one signal is the I of the other signal. So what happens is if one of these chains drift, it encodes both signals. They both experience the same phase noise from the LO. They both experience the same gain variation, everything. Graphically, it looks like this. So if the 2 paths are matched, the cal signal and the input signal look the same. If they're mismatched, both signals go through both paths, so they both experience the same amplitude distortion, but at different phases. So the cool thing is because the phase is preserved, and I squared plus Q squared doesn't really care about the direction the arrow is pointing, only the length of the arrow, you can still do the calibration. So this lets you observe the output or the input 100% of the time. Circuit-wise, it looks like that. We use transformer coupling stuff on the chip. It's pretty traditional. The hybrid up front is just a branch line coupler hybrid, nothing crazy. There's the chip. You can see the 2 LNAs, which is kind of strange looking. LO in the back, antenna up front. We did the test with a cold nitrogen, liquid nitrogen as the cold target, and then the regular air is the hot target looking at in the lab. And we did the measurement, and sure enough, with the calibration off, we have an NEDT of 8 in a bit. With the calibration system on, with those 2 paths canceling, we got about 1.65. So it's good, but it still sucks because it's still 3 times worse than what we need around here at JPL. The other more depressing thing is the NEDT without cal, that 8 Kelvin or whatever, that's even better than the one we built with the switch. So the switch is actually making things worse, not better, which is very interesting because it's actually the same LNA and everything that we use for both. All right, so sometimes you just have to give up and stop being smart, and that's what we do here. So we put an indium phosphide mimic up front at higher frequencies, and we just say, we can't win this drift thing, we can't win, so we're just going to push down the T-sys of the whole system by putting some nice mimic up front that pushes the noise figure down, and away we go. So we did that on the first one. We did it at W band, which is the O2 line, the oxygen line. So there's the chip. You can see on the left we have a noise figure, and then when you put the mimic in front, the noise figure gets a lot better. Well, these are mimics from NGC, and the value of performance is apparently very high, but it also works very well, so that's fine. And there you go. So we were able to do that. And here's some pictures of me. So I drink a lot of coffee, so I'm warm in the coffee place, which is fine. And then you take the background of these scenes and you can look at the variance of the temperature that's being recorded. That gets you the NADC directly instead of calculating it. So what you're looking at these are passive images, right? It's not some signal shining on them. It's just the things being warm and emitting radiation. So this is, half a Kelvin. It barely works, but it works for the most of the space science. Of course, it's only a W band, so we need to keep thinking. One of the lines that's most interesting to us is the water line, and there's a water line at 183 gigahertz, 183.310 actually. And this is a second version of that radiometer spectrometer front end that we did. And you can see, again, there's two nice indium phosphide mimics up front that make it all work. T-cis about 490 Kelvin to 500 Kelvin, depending on what frequency. At the water line, it's 490 something. Off we go. It's very nice. It works. It's compact. The whole thing's about a third of a watt. One of the interesting things we figured out here is the IF. We did a lot of work on the IF between the two generations of receiver. In the first one, what we had the IF being these open loop amplifiers. It's like a common source with some resistor junk on top, and you get an Allen time of about 6 seconds. But what happens is the gain of that is drifting between flicker, noise, supply, all the stuff, right? So if you go to a closed loop amplifier like an op amp, which is possible in 28 nanometer to get a gig or two of bandwidth, you can see the closed loop behavior because the device parameters are no longer in the gain equation, or the gain's less dependent on the device parameters. Suddenly the Allen time pushes out by almost a factor of 3. So just by that very, very small change, you can improve your NE delta T quite effectively. So the beauty of CMOS is you can do these closed loop structures. All right. We dragged the thing to the lab. We got a little chamber. We put some water vapor in. Again, very low pressure. And then you have liquid nitrogen in the background, very cold. So you have the contrast, and you don't have pressure broadening. And sure enough, you can see some lines. So we got water, and we got some other chemical that the lab uses, and we can see the lines there. So these are emission spectroscopy. It's very simple. A bigger example is the one at JPL that I contributed to, which is the Pizarro, which is a very, very big spectrometer. This is a 600 gig one. Obviously, we're not doing the front end in CMOS with this one, but we're doing all the support stuff around it. Like I said, we could never get the sensitivity of these gas mixers. So Pizarro has a nice silicon micro machine front end that Gadam and his team built. And then I worked on the back end and the synthesizer. So the synthesizer is an interesting topic for power. Before I joined JPL, it would look like this. At the top, it would have a 16 gig DRO, and it would multiply to oblivion, and the power would go up and up and up until you end up somewhere around 25 watts. Then we built a 30 gig CMOS synth to skip one stage, and suddenly the power is only 8 watts because you don't need as much amplification stage after stage after stage. Then we did a W-band one, and suddenly it's only 4 watts. And then we did a 200 gig one, and suddenly it's only 3 watts. All right, so one of the cool things I said is that radiation is ruining our day every day. So we build circuits like this and stick them inside all our chips, which are radiation sensors that tell us how much dose the chip has, and we use that information when we do the calibration. It's a neat trick. How it works is an I/O device and a core device, and you put a circuit in between, and you tune it so that their temperature coefficients cancel out, so it's not sensitive to temperature, but because they're different devices, their radiation profile is different, and then you can build a sensor by leveraging the rate of change of the threshold versus radiation, even though the temperature is canceled out. Cool. This is the W-band synthesizer that we did. It's pretty straightforward. It's a MASH 11111 fifth order, sigma delta, modulated, multi-stage noise shaping, fractional. Output power is about 4 milliwatts. This goes in a nice little box, and then it goes in the instrument. We use a WR10 output waveguide flange, pretty straightforward with a little probe to excite it. All good. This is the 200 gig one. The packaging is still a work in progress. Phase noise is pretty good, minus 80 something, minus 90 around there. Again, it goes on a little board, and there's a little waveguide coupler, and it just plunks onto all the millimeter wave blocks. It's kind of cool. Of course, we have to check them, so we go to the cryogenic world, we freeze these things and make sure they still work. And the neat thing is you can see all the little control settings and all the tuners that do the calibration changing as we cool the chip. And of course, the phase noise gets a little bit better when it's colder, but not by much. So that's kind of cool. We have to do radiation testing, so we put the chip in the irradiator, and again, we expose it to a high level of radiation. If we're doing Jupiter, maybe up to a megarad, and we look at what the knobs are doing, and we make sure that the phase noise is still acceptable, and that's our synthesizer. The other one we do a lot of is the back-end processing. So this is a spectrometer processor we did between UCLA and JPL in 2014. This was our very first chip. It's not exciting. It's slow, and it has about 2,048 points or channels. So it's not a super high resolution spectrometer, but it's something as a start. And the power was pretty low. It's about a watt for everything. So then we built a new one, which is the spectrometer processor. This is the one we use all over right now, which is a 8,000 point FFT, and then it's a 6 gig of samples, so 3 gigahertz bandwidth. It flew on the SLS, and it flew on the rectangle mission I'm going to talk about in a second. And right now we're working on a third generation, although it's killing us. There's going to be twice the bandwidth and twice the points. And it's in a 28 nanometer advanced, and we're dealing with flip chip, and it's all a lot of fun. Okay, so, I have some measurement. Cool. So yeah, the ADC is working. There's the ADC working. We haven't really gotten into the core yet. We're still doing that. So the Pizarro instrument as a whole, here's a test. This is what it kind of looks like. Again, you have a gas cell, low pressure, so you're not pressure broad, and liquid nitrogen, so you have contrast. You put the receiver there, you put the spectrometer there, you spend a month trying to get it working together properly, and then sure enough, you can get a line. So this is the red is what the water line looks like at 557. That's from your quantum mechanic model, and then your black line is what the receiver actually measured. So this is currently the lowest submillimeter instrument in NASA's portfolio. We're about just under 8 watts for everything, and we're as sensitive as any other instrument you could ever send anywhere. Cool. So some recent technology demonstrations to wrap up here that use all this stuff. One really cool one is camels. So if anybody knows, there's an instrument called MLS on the Oris spacecraft. It's 20 years into its 5-year mission, like everything else around here. It's being run a lot longer. It always works more or longer than we planned, and that's good because we get our money's worth. So MLS looked at a whole bunch of lines at a whole bunch of different frequencies, but there is a risk that at some point it is going to fall out of the sky and stop providing science. So we need a follow-on, and the follow-on is called CAMELS. CAMELS is a 340 gigahertz instrument that looks at all the lines down here below. There's a ton of them. There's waters, there's sulfates, there's pollutants, there's all kinds of cool stuff. So this is how it looks. The receiver is a MMIC-based receiver. Again, NGC provided the MMICs. Beautiful Schottky mixers, nice IF, everything made in-house at JPL. Then we have it in a cryostat because to get the sensitivity, we have to cool it. And the contribution from the CMOS side is these 2 back-end spectrometer processors. So those guys do all the processing on the IF of the receiver. We haven't flown yet, but we took it up a mountain and we pointed it straight up at the sky. And sure enough, we can see the mesospheric carbon monoxide, which is a very, very strong and high Q line that you can always see if you're above a couple of thousand meters of altitude. The pressure is so low up in the mesosphere that the CO line it's pretty pointy. There's no broadening at all. We also did some other measurements on different days. We saw some nice humidity. Everything's good. The gray is what you'd expect, and the green and red and other colors are what we measured. Because our IF isn't infinitely wide, we can only measure in these 4 color bands right now. We're going to be flying on the ER2 hopefully this year, and the instrument will go in that pod, and then that'll go up to 70,000 feet, and that'll be awesome if we get measurements. All right, next thing. So the one that I've been working on for the last year is the rectangle mission. So Theodore Reck, unfortunately, is no longer with us. He went to VDI, but when he was at JPL, we started this project. So I also couldn't find anybody else on the team whose name fit, so that's the name we went with. Rectangle. So this is a 180 gig and 550 gig spectrometer combo on a balloon craft. So basically, we took the receiver that I showed earlier that we did those lab measurements on, and we took the Pizarro type instrument, although we made some changes. The original was single sideband. This is actually a double sideband instrument because the LO was just too much. So sure enough, we took it out. We went to Fort Sumner, which is probably the most horrible place on earth. It's in New Mexico. They have one restaurant. It doesn't open on weekends. You have to drive 70 miles if you want anything else. There were snakes, there were scorpions. I'm still in therapy from it all. But anyways, we flew. So this is a couple looks at it. We put a parachute package together. We put the control package together. You can see my pilot. So we have to have a pilot. So we got the little green alien man and we put him in the box. Anyways, sure enough, we flew the mission. We launched on October 17th. That's the balloon craft going up. We flew pretty much all the way across the Texas Panhandle. So on the left, you can see something interesting. Our receivers don't have a cold load like a liquid nitrogen, like a jug. So what we do is we look at space to get the cold load, because space is cold, of course. The thing is, the atmosphere is opaque. So when you're down on the ground, the Y factor is almost nothing because you can't see through the atmosphere. Everything's warm. But as you get up and up and up into space, or near space, where the balloon goes, you can see the cold of space. So your Y factor gets better and better and better as you ascend. And that's how we check that the receivers are working in flight. Then we flew all the way across, and here there's a nice camera picture of what we got from the mission, which is the only picture that we collected, actually. And then on the right, we have one data set. This is a downloaded data set, so this isn't calibrated. The data we recover after is actually all calibrated, and we model it properly. This is just like the raw data coming down from the telemetry. So we can see a line, and you can sort of see the features that we'd be looking at: the pressure, the abundance, the velocity from the Doppler shift. All right, so then we crash landed very, very hard. My poor little green man has a metal bar through him. The spacecraft was a complete write-off. Everything is destroyed. That's the way it should be. So that's sad, but we got the data. So here's what we collected. This is not beamed down. This is what's on board, and then we process it after we get back to JPL. So the 94, so on the right, you have the simulated lines the simulated behavior we expect. This is the radiometric brightness of the water line, looking from zenith to nadir, so scanning from an elevation of 180 to 0. We think we're set up at about 94 degrees based on the IMU, so we expect this kind of a line. On the left is what we measured, so we have really, really good agreement between the two. And that's the first example of a CMOS chip doing an atmospheric sounding and measuring gases in the atmosphere. So, thoughts to take away on this: there's a lot of exciting places in our solar system to explore, but the power availability is not great, so CMOS makes sense for that. The key to the whole thing is understanding the science that you're trying to do and not just the technology itself, so you can make smart design decisions and come up with a system architecture that makes sense. The last one I'll throw out there is the laboratory experiments are only the first step. A lot of people like to work in the lab and get some quick measurements. It's good. But I've learned that when you go out and you suffer in the real world and the snakes are trying to eat you and everything, that's when you really learn what works and what doesn't work and lets you get to the next level and really build systems that work. So just acknowledge all the people that paid for all the stuff you just saw. It's basically NASA and JPL. And that's about everything I have to say this morning.
Okay, great. Thanks, Adrian. So we've got plenty of time for questions and answers here. So please feel free to go ahead and submit your questions, and we'll get Dr. Tang to answer them as we go. So the first one here is in the Dickey-free radiometer architecture. How do you handle the mismatch between the two receiver paths? So, for example, 0.007 dB mismatch seems to be very restrictive.
I knew that would be a question, so let's go back there. Okay, so the slides are still visible, right?
Yes.
Okay. So here's the thing. It's not about mismatch. So when people ask that question, they're always thinking about like the cal is one path and the signal is the other path. That's not really what's going on. Well, it's kind of blue and red here. So the blue signal, the one that you're measuring from space or wherever, that's going through both paths, right? It's going through the top path at 0 degrees and the bottom path at 90 degrees. The cal is going through the top path at 90 and the bottom path. So both guys are going through both paths. So if you think about the phasors here, so basically the I of one is the Q of other, right? And the Q of one is the I of the other, but they're both going through both. So this is what the phasor looks like. If you have a distortion in I of one channel, that becomes a distortion in Q of the other channel. So if you look at the right plot, the magnitudes are preserved even when there's mismatch in one channel. So the answer is it's not a concern about mismatch between channels because both signals are encoded with that mismatch. So you can still calibrate.
Okay. So I think you mentioned it a couple times, but there's a question here about the technology nodes that were used in some of these chips.
Oh, God. 65, 28, 40 nanometer TSMC, and the indium phosphide, I believe, is mostly 35 nanometer.
Okay. So a little smattering of all of the above. Any comments on pluses and minuses of those different technologies?
The 28 nanometer costs more money. So only use it if you have to.
Okay. How do you know if you have to?
How do you know if you have to? Usually my rule of thumb is if you're above W band, you can benefit greatly from 28 nanometer over 65. It's interesting. The 40 nanometer TSMC doesn't seem to buy you much over the 65 compared to the 28. So we don't use much 40 nanometer anymore. From a financial point of view, the 40 nanometer and 65 nanometer is almost the same. The 28 nanometer is a special case.
Yeah. Any exploration in even more highly scaled nodes?
So as you go beyond 28 nanometer, you get into the FinFET regime. And the FinFET regime, although interesting for speed, has a lot of side effects that come through the door with temperature and radiation. And my goal in life is to avoid those side effects.
Roger that. Yep. So how large of a team do you have there designing the CMOS circuits?
Well, we have me. I do basically most of the RF. We have 2 students at UCLA that do the Yan Zhang does the digital for all the spectrometers, and Rulin Heng is doing a lot of help on some of the analog mixed signal. And I formerly had a postdoc, Rod Kim, and he did a lot of the ADC work. But at this point in time, it is pretty much just me sitting here right now.
A lot of work for one person.
Can you tell JPL that?
have them listen to this webinar. Okay, so let's see. So here's another question on the impact of radiation on the different technology nodes.
Yeah.
Why does your radiation setup look like a Futurama robot?
Radiation setup. So an interesting full disclosure. This is not exactly JPL setup. This is a typical setup from the vendor that built JPL system. We obviously can't go in there and take a photo of the real one, but this is basically the idea. It's kind of tricky. You put cobalt-60 rods in this thing, and you have to do a bunch of dosimetry to figure out where to place your chip in the environment, and then you pull the rod out, obviously when you're not in the room, and you basically expose it to a certain number of rad dose at a certain dose rate. And some of the harder stuff, what you do is you move it around the room between tests so that you can not just get a dose rate, but a dose profile. So like, I don't know, if you're orbiting, I don't know, pick something. If you're doing like the Juno mission, where you have a high dose rate for a very short time, because, if you look at the orbit, it's very elliptical, and then it goes far away from Jupiter for a long time. So what they'll do is they'll move the chip in and out to simulate those effects. So the dose rate goes up and down. That's what that is. Again, let me stress, you can't be in the room during the test.
Yeah. Okay, there was some concern here about the captain. They called him Captain Jose. Will he be good for another launch?
Oh, Captain Jose. Captain Jose is the little... So I might as well say this on the webinar for the first time. I work at JPL, and I found a little unresponsive green man on a spacecraft wreck. But I put him there, so that's okay. He is okay. We sewed him up, and the metal bar was extracted from his torso, and he's ready for another flight this year.
Excellent. So that's some breaking news right there. Okay, so did you do any radiation tolerance testing on the circuitry for PLL and phase noise, and can you elaborate on that?
Yeah, I can do that. So I think I have plots and everything. So let's see. Yeah, so the phase noise on, this is the W-band one, I think. No, sorry, this is a 200 gig one. This is the data. The phase noise doesn't change much because the junction cap and the switching device and the inductor up top are really not the things you're worried about in a radiation test. You're more worried about like the bias being, like the current mirror down below changing ratio drastically. You're worried about any type of precision bias voltage wandering away. But we have a lot of knobs that deal with that. So, you know, the digital core sees with the sensor that it's off, and it will tune the knob to put the currents back. So effectively, you don't see much. A big part of the radiation strategy for these SOCs is to have a lot of sensors and then detect when that change occurs, whether it's a threshold change or a leakage current change or whatever, or some, you know, those are very device oriented, but you could have some very high level changes. I don't know, the ADC, INL or DNL drops or something. And then you kind of capture that and then do the adjustment with all the knobs, and hopefully it works.
Okay. Let's see. This is good. We're getting a lot more questions rolling in here. So Fmax measured for 28 nanometers is about 300 gigahertz. How did you manage to get gain around 600 gigahertz?
So, okay, that means somebody needs a picture. Which way? So the 600 gigahertz stuff isn't CMOS. I thought it was kind of maybe not super clear. So the front end is it's a gas Schottky, and then everything else is CMOS. Right, so the front end mixers on the left there, they're actually gas Schottky. It's only, you know, the LO is CMOS, and not even the high-speed LO, just the first couple of stages of the LO.
Right, hopefully that's clear, yeah.
Yeah.
Let's see, there's still some questions here about the different radiation effects. So from your experience, is SOI better for radiation hardness?
It's all, it's very dependent on where you're going. So if you're worried about heavy ions and stuff getting trapped in your chip and annihilating you, then SOI is probably a good choice, especially fully depleted SOI. But if you're going to Jupiter and you're about to get a gamma dose that basically changes the color of your chip because the glass on the nitride on the top is starting to burn off, then it really doesn't matter if you're bulk or SOI, you're still going to have a nightmare. There's varying degrees of radiation, and there's many different sources of radiation. So like the single particles, single event upset stuff, you have one whole way of dealing with that. When it's just like total dose and you're getting baked, you have a different way of dealing with that. But in general, you need to monitor the health of your SOC and then make intelligent decisions based on what your sensors are telling you. And the hardest part is making sensors that you can rely on in those terrible environments.
Okay, let's see. How long did it take to design the 200 gig PLL?
I think I started Friday and GDS was ready Wednesday or something around there.
Working 24/7?
Yeah, so usually, yeah. But to be fair, you know, it's not a scratch design. You start with the W-band one and rework it. So.
Right. Okay, yeah. So continue to send in questions. We still got some time here. Let's see. There's.
I do the space science questions too, so you don't have to ask just the circuit questions.
Yeah, that's a good point. Yeah. All right. Here's another radiation one. Radiation effects on locking of PLLs.
That's a good one. Again, you know, so it depends on the PL. But let's say you're doing an LC PL like I do. Generally, the VCO isn't going to change much. Where you'd have to worry is the charge pump, because the charge pump current is super sensitive to the dose. So what you have to do is you have to put a sensor that figures out the dose, and then you have to put a set of switches and some kind of logic that says when the dose goes up, the current has to go up to make for the current that disappeared from the dose. That's all.
Okay. Wow, that's a neat trick.
Yeah. This was all impossible until we figured out the embedded radiation sensor. Once we had that piece of IP that reliably measures the dose, everything gets easier because then you have a number.
Right. All right. Well, so I think we've answered the other lingering question here. Any other comments, Adrian, after hearing some of those questions?
I think I'm good.
You're good? Okay. All right. Well, so we can go ahead and close this out. As we said earlier, this session will be archived on the Society website at mtt.org, and all registrants will get an email reminder with a website address when that's available. For attendees who would like to receive PDH credits, please follow the link in the webcast view and use the code provided on the last slide of this presentation. And also, once again, I'd like to thank MTTS, who was our sponsor for this, and especially Dr. Tang for this excellent and informative presentation. Also, special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you, and have a great day.